All right, number 8 on the worksheet on average value. The velocity of an accelerating car is shown on the right. Estimate the average velocity of the car during the first 12 seconds. Okay, well, the average value of any, whether it's velocity or f or anything else, the average value is 1 over the width of the interval times the area under the curve, or the antiderivative of the interval. So we'll find the area under the curve, and then we'll divide by 12, and that'll get us the average value. And it says estimate, so I don't have a function, so I can't do an antiderivative and plug in limits. I don't have that option. It's going to have to be a geometry thing. And so, it doesn't specify right hand or left hand or midpoint or triangles so I think let's do 2 triangles, because I feel like that's pretty close, and then that's I guess that's not triangles. Those would 1 triangle and 1 trapezoid. There we go. I'll figure it out. Because I guess I could do 1 triangle, but I really don't think that would be very accurate. So let's do a triangle and a trapezoid, and I figure that's pretty close to good enough. So the triangle then is 6 times 50 is 300, divided by 2 is 150. And that trapezoid, its width is 6, its average height is 70 plus 50 over 2. So what is that? That's 60 is an average height. Times 6 is 360. So the average value is 1/12 times 150 plus 360. And that would be an okay safe stop for that question, except that we keep going and we really need to know a better answer than that. 150 plus 360 divided by 12, 42.5 units kilometers per hour. .5. Okay, that's believable. It started at 0, it landed at 60, but it's not. No, it landed at 70. It's not 35 because it's like concave down, so it covered more area than if it had just gotten straight there. So we'll say 42.5, but if you'd used a different method of approximation, you'd get a different answer. And as long as it was clear what you did, that would be okay. Part B, at what time was the instantaneous velocity equal to the average velocity? Okay, well, the average velocity is 42.5, so somewhere in there. Zoom way in. See where that graph, where 42.5 crosses the instantaneous velocity. Right there. So what is that? About 5 seconds. I don't know that we could get any more accurate than that. So approximately 5 seconds. It's hard to be any more accurate than that. And the mean value theorem guaranteed that location of that time was in between 0 and 12. All right, number 12. Speaking of 12. Using the figure on the right, find the antiderivative, or the area under the curve, from 1 to 6. Okay. rather than go piece by piece, I think I'm just going to count the squares, because they're all like 1 unit squares, and they're all either 1 or half. So 1, 2, 3, 4, 5, 6, 7. 7 and a half, because this one's a half. 8, 8 and a half. How about that for a method? Just count the squares. 1, 2, 3, 4, 5, 6, 7, 8 and a half. I think that's easier than, a trapezoid plus a trapezoid plus a trapezoid plus 2 rectangles. I mean, I guess you could do that, but when they're all divided up nice and neat, 8 and a half is fine. Average value on 1 to 6 would be 1 over 6 minus 1 times the integral from 1 to 6, which we already found. So 1/5 times 8.5. And safe stop, why bother? Leave it like that. Although, I don't know, if you want to see what that answer is, 1.7, to kind of see if it makes sense. So 1.7, that seems right. That seems like a good average value. It's definitely above 1, definitely less than 2. And it spent more of the time at 2 than at 1, so it's bigger than 1.5. I don't know, just trying to make sense of the answer. Number 13. Using the figure on the right, estimate. So another estimate. That means, best guess. Sketch in some triangles or count the squares or whatever you want to do. From -3 to 3. So -3 to 3. Well, let's see. How do we want to do this? You can go column by column, because I'm trying to think of a reasonable way to get a decent answer without making it take forever. Tell you what, I'm going to go column by column here. Say this column is a little bit more than 1, maybe even 1.5, right? Because it's almost all of this square and then like a little more than half of that square. So -1.5 for that column. It says estimate, so I'm allowed to do this. How about this column? What would you say the area of that column is? 2.5. I'd say 2.5, 2.6, whatever, something along those lines. Negative though again, so be careful. How about that guy? Okay, -2.1 or just -2, either one. But I heard -2.1 first, so we'll go with that. Because it's maybe a little bit more than 2. Still negative though. How about next column? Negative points. Oh, let's just keep it to 1 decimal. Let's not pretend that we're that accurate. -0.8, I'll buy that. Because it's less than 1, right? If I took this little bitty triangle and moved it over here, it wouldn't fill up the void, the missing spot. So less than 1. How about that next triangle? It's less than 1. Yeah, the triangle. So half, 0.6, either one. What about the next one? 1 point a little bit. 1.1. I don't know that that's 1.2. We'll go 1.1. And the last one, I'm running out of colors. What'd you say, Piper? 0.2. You don't need to do that last one. Oh, you're right. Good call. We were supposed to stop at 3. Yes, so I don't need to include that last one. Thank you. So I could just write all those out, but I don't. Let's get an answer because we may need to use them anyway. Negative 1.5 plus negative 2.5 plus negative 2.1 minus 0.8 plus 0.6 plus 1.1 negative 5.2. Okay, I mean, I guess that's fine. It's definitely negative because there's more negative area than there is positive area. Which of the following average values is larger? Well, from negative 3 to 3, that would be 1/6 the integral from negative 3 to 3. So we just did that one. I mean, we did the integral part anyway. So I'll say negative 0.9. That's rounding, but we've been estimating anyway, so hopefully this isn't close and we'll be able to tell which one's larger. From 0 to 3, that would be the 1 over 3, the integral from 0 to 3. And now I'm glad I broke it up this way, because now I can do the integral from 0 to 3, because I'll just add up those three values. Negative 0.8 plus 0.6 plus 1.1. I'm pretty sure I know which one's going to be bigger. Which one's going to be bigger? 0 to 3. Why 0 to 3? It's positive is the easiest answer.
Would you have to write it out like that, or could you just say like, oh well, it's obvious that negative 3 degrees, or yeah, it's negative, and then 0 to 3 is above the line, so it's positive.
Yeah, you could say that. Because it's clearly negative 3 to 3 is net negative, and 0 to 3 is net positive. So 0 to 3 is going to be greater because it's positive. Heath?
Can you explain why you put the 1/6 and the 1/3?
Yes, because the 1/6, so this is the area under the curve. But this one asked me for average value. So average value means I need to divide by the width of the interval. So the integral tells me the area, but average value means divide the area by the width to get the average height. Number 14. The average, 14, not 15. A bar of metal is cooling from 1,000 degrees to 20 degrees. The temperature of the bar is given by this formula. So I hope this is a calculator problem. Find the temperature of the bar at the end of 1 hour. Well, so this is the temperature of the bar after t minutes. So this is kind of just a units thing. H of 60. And I don't have to show the work, because this is going to be a calculator problem for sure, because there's going to be crazy stuff. So on a calculator problem, if you say H of 60, that means you're telling the grader, I'm going to take the H formula and plug in 60, and I'm using my calculator. So I don't need to show any more work than that. So there's H of 60. 22.429 degrees C. Word problems mean just check and see if that makes sense. So if it starts at 1,000 degrees, that's really hot. But sitting in a room for an hour, and it's a metal bar, so metals don't hold their temperature really well. So I would say that's believable. Seems a little low maybe, but at least it's not lower than 20. I didn't expect it to be 987. So lower than I thought, but I think still reasonable. Find the average value of the temperature over the first hour. So that would be 1 over 60 to get the average. So 1 over the width times the area. Since you're going to the calculator and h of t is defined, then you could just write that and then write the answer. Math 9. 0 to 60. 20 plus 980 e to the negative 0.1 x dx. Why am I getting 11,000? Why? That doesn't seem right for an average temperature.
Multiply by 60.
Yeah, I forgot to divide by 60. That's kind of a common mistake on these because you get so focused on the formula and then finding the right buttons on the calculator and making sure everything is matched up and lined up right that you forget to divide by 60. 182.928. See if that makes sense. So the average value of the temperature, 182. Okay, well I didn't expect the average value to be like halfway between 20 and 1,000 because if it went straight from 1,000 to 20, then the average would be the kind of a linear thing, but it's not a linear thing. It's like that. So I think I can believe that it's closer to 20 than it is 1,000 because initially it drops so fast, then it kind of levels off. And I think I just answered part C. Is your answer to part B greater or smaller than the average of the temperatures at the beginning and end of the hour? Well, smaller, right? Because it's saying, how does it compare to 22 plus 180? No. 1,000 plus 22 divided by 2. I don't even like that it asks you to do that because that's not the average temperature. But that's what some people will do. So 511 is the middle of the temperatures between 0 and 60, but that's not the average temperature. Explain this in terms of the concavity of the graph of H. Well, it's concave up. And so I can tell by looking, I don't have it memorized that concave up really means anything, but the fact that it's concave up sort of pushes more area, pushes it lower, right? If it had just gone straight there, then the average would have been whatever it was, 511. Instead, our average was 182, so something more like that. And that is how things cool. That's Newton's law of cooling. I think we get there later, how to come up with that equation. But things don't cool down linearly. They cool down exponentially. All right, but the big thing, the big deal from yesterday is that the average value, I'll write it one more time down here, 1 over b minus a times the integral from a to b, f of x dx. And it happens somewhere between a and b. That's the intermediate or the median value theorem part. C is somewhere between A and B. That's the median value theorem part. So average value, that's what it is. MVT tells you that where it happens, well, somewhere on your interval. Which certainly makes sense in terms of like the problem we just did. Like the metal bar is cooling. The average value was 182. Where did that happen? Well, somewhere between 0 and 60. Like, I don't know where exactly, but it didn't hop around and do something crazy. Like, somewhere between 0 and 60, the temperature was actually 182.